Hello, this is for week 12, probably going to be the only lesson video for this week, as on Thursday you will be taking exam 2 for me. I didn't hear from anybody about not being able to take the exam from 9:30 to 11 this Thursday, so I'm assuming that everyone, because I will email you your exam at 11, and you have an option. You either print it out if you want to, or you just copy it down on a separate sheet of paper and make sure you work on all the problems, scan and submit it on Canvas for me. So that link is available right here. I did post the practice problems. Several of you emailed and asked about it. So it's going to be very similar. So you will have about 13 problems, starting with 2.1, some of these exponentials and finding the I really need you to try all these problems before you get the actual exam on Thursday morning, so that you can ask me questions about it. Okay, no one emailed me about any questions on any of these problems yet, so I'm assuming that you're all okay with these. But you still have time. If you want to email me tonight or Wednesday morning, Thursday morning will be we won't have time to do that on Thursday morning, because Thursday at 9 o'clock, I'm going to send you the exam at 9 o'clock, so that if you want to start early, you can start early. But about 13 problems, very similar to all the problems that we went over together. I really want you to try these, and I need you to let me know if you want to see how to do certain problems. And I gotta tell you, number 13 is something that we're about to go over together. I'm thinking, though, the problem that I'm giving you is open top cylindrical container. I'm thinking about maybe changing that to a closed top cylindrical container and keep everything about this problem the same and see if you can do that one. But that's it. That's it for you. And then I do have the solutions right there. So really want you to try this. Since I'm making 3.5 homework extra credit, I'd rather have you try this and prepare for your exam too. I know it's take home. I know it is open note, open book, but you will still need to show me work on all your problems, because you can get the answers online. But I'm going to ask you, well, if you're using these online calculators to get your correct answers, I can't stop you, right? But you gotta show me enough work to support these answers, okay? So please try not to use those online calculators. But, the thing is, I won't know. But I will also ask you to please make sure to show all the work. If you just write down the correct work, then I'm just probably going to give you like 1 point for getting the correct answer. But if there's no work, I won't give you the full credit, okay? So remember, try these. Ask me if you have any questions. Hopefully today, tomorrow, I get some emails about any of these problems. But the goal for 3.5, because I'm making this homework just an extra credit. Looks like somebody already kind of started on it. I just opened it. But I'm going to go over only 3 examples with you. That's going to take us a long time. But that's 3 out of 7 that you're going to try on your own on your extra credit homework. If you want to see more of these fun optimization application problems, let me know, because I think the ones that I'm going over with you are similar to, similar to number 1, 2, and 6. But if you want to see questions 3, 4, 5, or 7, I can go over those with you too. Just let me know. But I think these 3 will be enough. And I'm going to put 1 optimization problem on your take-home exam this Thursday. And it's going to be either example 1, 2, or 3. We'll do all these together and we'll kind of decide. I'll decide at the end of this video. So, it's going to take some long time, but we can do this. These are pretty fun, okay? Alrighty. Let me open that on my notepad. Where's my notepad? Okay, here it is. We're still doing optimization. We're finding the absolute maximum and absolute minimum values. But right now, we're working with word problems. So the math that you need, the calculus that you need to solve these problems, you already got it last week. 3.4, when you were asked to find these absolute maximum or absolute minimum by first finding the derivative and all, you do know the skills to solve these problems, but they can be pretty confusing and challenging because now we're going to work with some of these formulas. But let me start with example 1, okay? This is the one that you will see on your practice exam, and I kind of like it, but like I said, I'm thinking about changing that open top part to a closed top part on the actual exam, but we'll decide. An open top cylindrical container is to have a volume of 2,197 centimeters, cubic centimeters. What dimensions, radius, and height will minimize the surface area? Now, let's try to draw a picture first. Let me try to draw an open top cylindrical container. It's a cylinder, like a soup can, like a soda can. Let me draw it. So I'm gonna have my circle right here. Oh, I am so good at drawing a cylindrical, oh, not a dotted line. Oh, that looks perfect. Oh. Okay, but what you know is that the bottom, this is radius. That's a circle, so I'll call that radius. And I know how tall this can or a container, that's going to be the height. So we know that we're trying to design a cylindrical container, but that has to have a volume of 2197. So let me write that down, okay, because that has to be set. We have volume is equal to 2197 cubic centimeters. We call that the constraint. That's a restriction. We can make this cylindrical container really, really tall, like something like this, or really, really wide, but very short. Doesn't matter, that looks like a cheese. But the constraint or the restriction here is that it better have a volume of 2197. But the goal is to minimize the surface area, okay? So what I'm gonna do is I'm gonna write down the volume formula for cylinder. And if you're not sure about these formulas, you can look it up real quick. But the volume of a cylinder is going to be volume, it is pi r squared, that's for the area of the circle in the base, right? Times height. That's the volume of a cylindrical container. Now what we know is that this is equal to 2197 pi r squared h. So that's what we are given. That's the only thing that we know about the cylinder. But notice we got two unknown variables. Let me circle these unknown variables. Guys, pi is just a number. Pi is 3.14, so that's not a variable. But we don't know what r is, and we don't know what h is. So what we're gonna do is we're gonna write a function for a surface area, but we better only have one unknown variable. So what I'm gonna do real quick is I'm gonna just solve this volume equation for whichever looks easier to you. I think well, if you want to try to solve this for radius, you have to divide by pi h and take square root. It's much easier to just solve for h, because look what I can do to both sides. I can divide both sides by pi r squared. Then what I get is this will just cancel out, right? We get that height is equal to 2197 divided by pi r squared. So we wrote height in terms of radius, and we'll use that when we write the surface area. Now, why am I talking about surface area? Because they want you to minimize the surface area. So just like how we know the volume formula, we can look up the surface area formula online. Well, let me try to draw a net. Imagine cutting this cylinder, like right here, cut it, and then opening it. Let's cut this and open this. What you're gonna get is you're going to get a rectangle, You'll get a rectangle. And then we're gonna have a circle. All right, use your imagination. Imagine we're folding this piece right here. We're not folding, we're like, how do I say? But if you open up the cylinder, you will get a picture like that. This is the bottom, right? This is the bottom right here. I'll call it the base. And then this side will make it the lateral, the piece, like the side of the can. But notice we will usually have a top piece right here, right, to make it a complete cylinder, but they did call it open top, so I know I don't have a top right there. So this is going to be the net of the cylinder. So if I try to write the surface area of this, the surface area is going to be, first I know how to find the area of this circle. Know that the radius is r, and for right now we'll call this h for the height. The area of this circle is pi r squared, right? So I'm gonna add this pi r squared plus, now I need to find the lateral area. What is the area of this rectangle, right? An area of a rectangle is just length times width. I do know that the width is going to be h, but how long is this piece right here? Now that is the circumference. This is the circumference of this circle. Circumference of this circle. Okay, and circumference of the circle is 2 pi r. Okay, so what we know is that this length is 2 pi r. So if you find the area of this rectangle, you will do 2 pi r times what? H, right? So the area of the rectangle is what we just found, 2 pi r h. And the area of the base, the circle, is pi r squared. If you add them together, that's what we call the surface area. Say that if I ask you to try a problem on your exam where this container is not open top, like closed top, you have a circle on top of it, then what's the only difference? You're just going to have to stick in 2 in front of it, right? Because you're going to have 2 circles instead of just 1 circle. But for our problem that we're going over right now, it's an open top. So this is a perfect surface area formula. Let me make this a little bit smaller so that I can use the room down there. All right, ready? Now what we're going to do is we're going to plug in the h in here. Because notice I have r, that's an unknown variable, and r and h. I got 2 unknown variable in the surface area formula, and I just need 1 variable. So let's substitute the h in here. Now let's plug in this h into this h. Ready? So, and from now on, let me just call it the surface area. I'm going to give it a function name. How about I call it S of R? Why is it R? Because my input variable is R, radius. Usually it's like f of x, but I call it surface area in terms of radius. All right, let's write this down. Pi r squared, that one stays the same, right? Plus 2 pi r times, now, this is where we're going to change the h into 2,197 over pi r squared. Is everybody okay? Okay, I just did my substitution. Now, some things will cancel out. Notice things will cancel out. Surface area in terms of radius is going to be pi r squared plus, we'll cross out some things that will cancel out. Pi is canceled out. One of the r's canceled out here. Therefore, I'm going to have to multiply 2 times 2197 and put that over r. Let me get a little calculator. Whoopsies. 2 times 2197 is 4394. So write down 4394 Notice everything kind of got canceled out except for this R right here over R. Now, we wrote the surface area formula in terms of radius. Guess what we have to do? We're doing this because we want to find the absolute minimum, right? What I'm going to do here is I'm going to go ahead and take the derivative. Let's differentiate this S of R so that we can find the critical values, right? So S prime of R, oh, no. Before I get there, let me try to rewrite this S of R. I like pi r squared, but it's gonna make it easy for me to take the derivative if I write the second term as 4394 times r to the negative first power. Wouldn't you agree? And then we take the derivative of this. What's S prime of R? Well, let's take the derivative in terms of radius, okay? So pi is just a number, so you bring down the exponent of 2. So that will be 2 pi r. Oh, hello, 2 pi r right there. And then you multiply negative 1 times this number right there. So that will give you a negative 4394. But now, the exponent for this radius is negative 2 because you have to go down by 1. Critical value happens when the derivative is equal to 0 or when the derivative does not exist. And what I'm doing is I'm writing this as the second term as a fraction so that you can see r cannot be equal to 0, right? Because if r is 0, this fraction will be undefined. And then that's when the derivative does not exist. So of the first critical value, this is my moment. I'm going to write down all the critical values, okay? Notice if r is equal to 0, then the derivative does not exist. So r equals 0 is mathematically the critical value. But here's the thing. Can I have a radius of 0 and still have an open-top cylindrical container? I mean, of course, that's definitely going to minimize the surface area because I'm not going to have any cylindrical container, right? But will that have a volume of 2197? I mean, if I plug in 0 in here, what will be the height? 2197 divided by pi times 0 squared. I'm not going to be able to have a height. So if the radius is 0, the height will be infinitely big. That's not going to work. So even though critical value, I mean, that's when the derivative is undefined. We can't have a radius of 0 in the cylindrical container. So throw out that r equals 0. So what's the second case? What we now need to check is when does that give you, when does that derivative equal to 0? So set this equal to 0 and let's solve for that. Set 0 equals 2 pi r minus 4394 over r squared. Let's solve this. I'm going to add 4394 over r squared to both sides and get 4394 over r squared is 2 pi r. Notice I'm trying to solve for radius here, right? I got radius on both sides. So my next step, what I'm going to do is I'm going to multiply both sides by radius squared. If I do that, guess what happened? This radius squares, they cancel out, right? Leaving me with 4394 equals 2 pi r to the what power? To the third power. Now I can solve this for the radius. Divide both sides by 2 pi. Radius cubed is equal to 4394 divided by 2 pi. That means radius is going to be cube root of 4394 divided by 2 pi. Now that's a critical value. How do you know that this will be the local minimum or the absolute minimum in this case? Remember the second derivative test? Let's bring that. Let's do that real quick. Second derivative test. Now, in order for me to do the second derivative test, I need to find the second derivative, right? So going from that first derivative, let me go ahead and find the second derivative. S double prime of radius is equal to 2 pi plus, now I'm multiplying 4394 by 2. 8788 pi r raised to the negative third power. I'm going to plug in my radius in here. What's S double prime of that critical value? Cube root of 4394 over 2 pi. You know what we're trying to check, right? We're trying to see if this comes out to be positive or negative. 8788 times cube root of 4394 over 2 pi. But we're raising that to the negative third power. So what's that going to be? No, it's too much writing. Equals. Now, I'm just going to go ahead and type this in my calculator real quick because you know what? What we want is we just want to see if that sign is positive or negative. You see what I mean? So try to type that in your calculator too. We're just going to get like a decimal. I don't really care to get the exact form. But what will happen? I'm typing this. Give me 1 second. You type this too. 4394 divided by 2 pi. I wish I can show you what I'm typing in my scientific calculator. Negative third power. Guys, what I got is 18.85. 18.85. That number doesn't mean anything, but this comes out to be, the thing that it came out to be a positive. This came out to be positive. What does that mean? This means this graph will be concave up. Concave up. At that point, which implies r equals cube root of 4394 over 2 pi is where the minimum happens. Oh, super awesome, because weren't we looking for the R value, the radius that will minimize this cylindrical container surface area? So this is very good. That blue writing that I just did, we just confirmed that this is where the minimum happens. So we did a lot of things just now. What did they want? I gotta go back and double check. They said what dimensions, radius and height will minimize the surface area. Oh, guess what? I got the radius already. The radius is going to be cube root of that mess. Now, it's probably time for us to give them a approximate decimal answer. How about you type that in your calculator? Let's give them the radius. What is cube root of 4394? Oopsies. Cube root of 4394 divided by 2 pi. The radius is approximately 8.88. What was the unit? Inches? Centimeters. Centimeters. So we got the radius. That's going to minimize. This radius will minimize the surface area. Now remember, we do have a function that solves for height. Okay, I'm going to find the height now. Height was, what was it? 2197 divided by pi r squared. 2197 divided by pi r squared. Let me double check if I wrote it down right. 2197 divided by pi r squared. Now we're ready to find the height. And that's going to be 2197 divided by pi times, now we just found what the radius is, 8.88 squared. And that's going to be approximately, and that's where we plug this into our calculator, 2197 divided by pi times 8.88 squared. And that got me 8.88 centimeters again. And you know, it's a very reasonable thing for you to think about. The radius and height came out to be the same. Will this be the case all the time? Well, found out that the problem that I asked you to try on your practice test, let me show you the answer. This was the same type of problem that I wanted you to try on your own. Number 13 on the practice test. Sorry, this one right here. Open top cylindrical containers. The exact same problem, but I just changed the volume to 729 cubic centimeters. And the answer for number 13 is radius is 6.5 and the height is 6.15. They're different. So the fact that it came out very close in the very example that I just went over, you can't say that they have to be exactly the same all the time. So, but this was, I consider it to be the little bit shorter problem of these optimization application problems. But that was one of them. And my goal is to go over maybe 2 more like this. And then go over more if you email me about other examples. But this is similar to, I believe, your number. Let me go back and double check. After watching this video and understanding what just happened, you are ready to try number 6 on the extra credit homework. Okay? All right.